Friends, in my last video, I was discussing about the symmetry and how to find out the point group of a particular molecule. Now, we shall discuss about group theory. Now, group theory is an important concept. Who has introduced that group theory? Now, E. Galois in 1811 to 1832 developed the fundamentals of group theory. Now, this is the E. Galois who has invented this fundamentals of group theory. A branch of mathematics applied to any set of elements which obey the necessary conditions to be called a group. Now, for example, any particular point group, it would consist of number of symmetry elements. A set of symmetry elements, that is called point group. Now, point group which consists of the symmetry elements, all the symmetry elements, they must satisfy the necessary conditions, and these conditions to be called a group. Okay. So, for example, C2V point group. Now, C2V point group, it would consist of 4 symmetry elements. Now, 4 symmetry elements like E, C2, sigma V XZ, and sigma V YZ. I will discuss later on. The C2V point group, it consists of E, C2, sigma V XZ, and sigma V YZ, 4 symmetry elements. Now, these symmetry elements, they must satisfy the necessary conditions to be called a group. Now, chemists use a subset of group theory that is called representation theory. Now, we as a chemist, we have used only the subset of the group theory that is called representation theory. So, we should focus on representation theory. Okay. Now, symmetry operations and matrices. Now, in my earlier lectures, we have discussed about the symmetry operations, E operations, then the rotation axis, mirror plane, sigma V, sigma S, sigma D, and improper rotations. These are all some symmetry operations. Now, how to represent symmetry operations in terms of matrices? So, how to define all these symmetry operations in terms of matrices? That we shall discuss. So, how the symmetry operations change the Cartesian coordinates of a molecule. Now, previously we have, for example, this is the H2O molecule where this is oxygen and these are the 2 hydrogen. Now, after performing any operations, either C2 operations, okay, or sigma V operations, so what should be the position? What should be the position of these atoms after performing each operations? Now, instead of checking the positions of these atoms, we have to focus on these Cartesian coordinates. So no need to focus on these atoms. Now we will be concentrating towards the position of these Cartesian coordinates, X, Y, and Z. Okay. So for example, if I perform C2 operations, now where is C2 situated? Now, as we know that C2, this is C2, okay? It passing through the center of water molecule. So this is oxygen, okay? And Z axis, which is collinear with the C2 axis. Now, if I perform cyclic operation C2, so after 180-degree rotations, previously we have focused on these hydrogen atoms. That means this H2 comes over here and this H3 comes over here. Now, no need to concentrate towards this H2 and H3. Now, after performing that C2 operations, what should be the positions of y, x, and z. What should be the position of these Cartesian coordinates after performing each operations? What is the position of x if x becomes minus x? Or y becomes minus y, or z becomes minus z. So we have to check the position of x, y, and z. Okay. So for example, on performing E operations. Now if I perform E operations over here, if I perform E operations, so what is the position of x, y, and z after performing E operations? So we know that E operations, that means no change is made in the molecule. So the positions of x, y, and z remain as it is. Therefore, x, y, z, after performing E operations, x becomes x, y becomes y, and z becomes z. So no change is made, right? So all these x, y, and z remain as it is. However, on performing C2 operations, if I perform C2 operations, so sorry, if I perform C2 operation, this is C2, it is collinear with the z-axis, okay, and it passing through the z-axis. In water molecule, it has bent-like structure, and this is the C2 imaginary axis. If I rotate it at 180-degree rotations, after 180-degree rotations, H2 comes over here and H3 here. So this is my C2. So in the water molecule, this is the C2, which is situated on the z-axis. So z-axis situated into the C2 axis. Now what will happen after performing C2, after 180-degree rotations, what will happen? X becomes minus x. Y becomes minus y. X becomes x, y becomes minus y. However, z is situated into the C2, therefore the positions remain as it is. Okay. So the point x, okay, that means the point which should be on the opposite directions after performing cyclic operations. Okay. So x becomes minus x, y becomes minus y. However, z becomes z. So look at this. So x, y, z Cartesian coordinates after performing C2 operations. What is the position of x after C2? Then it becomes minus x. What is the position of y? Y becomes minus y. And z, it becomes z. On the other hand, sigma v x z. Sigma v x z. If I perform sigma v x z, sorry. This is my sigma v x z. So this ball itself we consider as sigma v x z plane. So it divides the molecule into two halves, both the halves which are mirror images of each other. And this sigma v x z, which consists of x and z axis, which are situated into the plane. However, y, which is perpendicular to this plane, sigma v x z. Okay. This is my sigma v x and z. This is sigma v xl plane. Now it consists of z and x axis. They are situated into the plane. However, the y, which is perpendicular to this plane. Therefore, after performing sigma v xl, the position of y, it becomes minus y, because उसका reflection कहाँ पे होगा? Back side पे आएगा. While we put the mirror plane sigma v xl, so say y coordinates का mirror image backside में आएगा, therefore y becomes minus y. So here you can see that sigma v x z, x becomes x because x is situated into the plane, their position remains as it is, therefore x becomes x. Y becomes minus y because it is perpendicular to this plane, therefore backside way, therefore y becomes minus y. And z becomes z because z is also situated into the plane, therefore it becomes z. So after performing sigma v x z, so x becomes x, y becomes minus y, and z becomes plus z. Same way sigma v y z. Now we perform sigma v y z. Now while we perform, sorry, like that. This is sigma v y z. Now this sigma v y z, y and z axes which are situated into the plane. However, z which is perpendicular to this plane. Okay. So while we put the sigma v y z plane, this is sigma v y z plane. So what will happen? The x which is perpendicular to this plane, therefore the x becomes minus x. However, y and z, they are situated into the plane, therefore their position remain as it is. So x becomes minus x, y becomes y, and z becomes z. So you might be understood about this positions of x, y, and z after performing each operations. Like C2V point group, it would consist of 4 symmetry elements: E operations, C2 operations, sigma v xz, and sigma v yz. So while we perform one after another, so what should be the positions of x, y, and z that we have discussed earlier? Yeah. So in this section. Okay. A combination of 2 operations can be shown as follows. That means if I perform C2 operations followed by sigma v xz. So look at this. The 2 operations. Now first, if I perform C2 operations, now C2 is situated it passes through the z axis. So z is situated into the C2. So while performing C2 operations, cyclic rotations, after 180-degree rotations, x becomes minus x, y becomes minus y. So here after C2, the position of x is minus x, y is minus y, but z is there. Why z is there? Because z is situated into the C2. Now same way, while performing sigma v xz after C2, so what will happen? Now minus x, okay, and minus x and z, they are situated into the plane. Now after C2, x becomes minus x, y becomes minus y, and z is equal to z. Now followed by the second operation, that is sigma v xz. Now while putting the plane where minus x and z remain as it is, however minus y, now again it get back to plus y. So here you can see that minus x become minus x, minus y, now it becomes plus y, and z is equal to z. So this is called sigma v yz. Okay, now matrix. So how these symmetric operations that would be represented in terms of matrix. Now before we proceed towards the symmetry operations that would be represented in terms of matrices. Now what is matrix? Now matrix is an array of numbers arranged in rows and columns. So these are the rows and these are the columns. So number of columns are there and number of rows are there. Okay. So this is 6 into 6 dimensional matrix. Now on the diagonal line, so this circle which indicates that these are the diagonal elements, starting from the top right corner to up to the bottom left corner. Okay, so this is the diagonal elements A11, A22, A33, A44, AMN. These are the diagonal elements. Okay. Now transpose of a matrix. Now, what do we mean by transpose of a matrix? Now, suppose you are given a matrix like A matrix, where the values are 1, 4, 6, 2, 7, 8, and 9, 3, 5. Now, if I carried out the transpose operations or transpose of this matrix, what should be the result of this transpose of this matrix? So, after performing transpose operations, so transpose of a matrix is nothing but row is converted. Row is converted into column. So this row is converted into column. So 1, 4, 6, now it becomes column. Okay. Second, 2, 7, 8, now it becomes column. And 9, 3, 5, so now it becomes column. So transpose operations or transpose of a matrix is obtained by replacing every element Aij with element Aji. That means row is converted into column. So in the previous matrix, in the original matrix, they are situated at the row positions. Row now it converted into column. So 1, 4, 6 now it becomes column. That is called transpose of a matrix. Okay. Now symmetry operations in the matrices form. So how the symmetry operations like A operations in case of C2V point group, it would consist of 4 symmetry elements. So all of you just keep in mind that C2V point group, it consists of 4 symmetry elements. Which one? E, C2, sigma V XZ and sigma V YZ. Now all these symmetry operations, they are represented in terms of matrices. So how the each symmetry operations that would be represented in terms of matrices. Now E matrix. Suppose we have to derive the E matrix. So how can we derive the E matrix? Now consider the transformation of a general point defined by x, y, and z coordinates. So these are the 3 coordinates x1, y1, and z1. Initial before operations. So these are the 3 coordinates. Now if I perform E operations, and we are getting the final coordinates x2, y2, and z2 after performing E operations. But we know that since E is a leave it alone operations, so no change is made in the molecule. So their positions of x1, y1, and z1 remain as it is. So therefore we can say that E is a leave it alone operations, no change is made in the molecule. So their coordinates x2 is equal to x1, y2 is equal to y1, and z2 is equal to z1. No change is made. Okay, so they are remain as it is. So x2, y2, z2. So x2 is equal to 1 into x1 plus 0 into y1 plus 0 into z1 on x-axis. y2 0 into x1 plus 1 into y1 plus 0 into z1. And for z2 is equal to 0 into x1 plus 0 into y1 plus 1 into z1. So in terms of matrices, so x2, y2, and z2 matrix is equal to 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, and 0, 0, 1. So this is E matrix into x1, y1, and z1. So E matrix, what is the value of E matrix? The E matrix which could be represented as the value of E matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1 in C2V symmetry. Now sigma matrix. So what is the value of sigma matrix? Now to work out the matrix for reflection plane, simple reflection plane, it is considered to lie along with one of the principal principal Cartesian planes in xy, xz or yz plane. So we have to imagine that mirror plane or reflection plane which is situated either in sigma xy, sigma xz or sigma yz. Now these are the initial before operations. These are the three coordinates x1, y1 and z1. If we perform the sigma reflections, after performing we are getting the three new coordinates x2, y2 and z2. Find after sigma reflections. Now note down that the changes of for reflection in sigma xy plane. So reflection plane, it would consist of x and y. So what is the positions? The z becomes minus z. So here we can say that x2 is equal to x1 because x and y, they are situated into the plane. However, z which is perpendicular to that plane, therefore z2 is equal to minus z1. So x2 is equal to x1, y2 is equal to y1, but z2 is equal to minus z1. So on expanding three-dimensionally, so we can say that what is the value of x2? x2 is equal to 1x1 plus 0y1 plus 0 z1. What is the value of y2? y2 is equal to 0x1 plus 1y1 plus 0 z1. What is the z2? z2 is equal to 0x1 plus 0y1 minus 1 z1. Now in terms of matrix, that means x2, y2 and z2 is equal to 1 0 0 0 1 0 0 0 minus 1. So what is the value of sigma xy matrix? That is 1 0 0 0 1 0 0 0 minus 1 x1 y1 z1. So this is the value of sigma xy. Same way, what is the value of sigma xz? Sigma xz, that means this plane, it would consist of x and z axis. They are situated into the plane. However, y which is perpendicular to that plane, therefore y becomes minus y. So x2 becomes x1, y2 becomes minus y1, and z2 becomes z1. Look at this, sigma v xz. So 1 0 0 0 minus 1 0 and 0 0 1. And sigma v yz, that is y and z axis, they are situated into the plane. However, x is perpendicular to that plane. Therefore, x2 is equal to minus x1, y2 is equal to y1, and z2 is equal to z1. Therefore, minus 1 0 0 0 1 0 0 0 1. This is the matrix for sigma yz. Same way, we can derive the matrix for I matrix. So here we are least concerned with this matrix. So we just forget about this. Now, an important one, that is, it would be easy to define the matrix for E operations, okay, or for sigma operations, or for any kind of other operations. But for cyclic rotations, or rotation axis, it would be a very difficult task to define the matrix, CN matrix. So how we can derive the matrix, CN matrix? First, we can focus on anti-clockwise rotations. That means the cyclic rotations anti-clockwise. Okay. Now look at this. Let CN axis be collinear with the Z axis. CN axis, that would be collinear with the Z axis and designated as CNZ. Okay. Now in Cartesian space, a Cartesian space where a point P1 with its initial coordinates x1, y1 and z1. So here you can see this in a Cartesian space, a point P1 with its initial coordinates x1, y1 and z1. These are the initial coordinates. Then C2 which is situated on the z-axis. Now a line joining the point P1, that is called vector R. This is called vector R. Okay. A line joining the point P1, that is called vector R. Now when rotation is carried out about the z-axis, now we have already discussed CN axis is collinear with the z-axis. So z-axis situated into the C2, right? So when rotation is carried out about the z-axis by an angle theta, so if I rotate in an anti-clockwise directions, if I rotate in a anti-clockwise directions, if I rotate in a anti-clockwise directions about an angle theta, this is about an angle theta, we can get the new point that is called P2 with its final coordinates x2, y2 and z2. Okay. So again I repeat how to derive the Cn matrix in an anti-clockwise rotations. So Cn axis, it would be collinear with the z axis and designated as Cnz. So in a Cartesian space, a point P1, this is a point P1 with its initial coordinates x1, y1 and z1. A line joining the point P1 that is called as vector R. Okay. Now, if I rotate the z-axis, in anti-clockwise directions, so what will happen after anti-clockwise directions about an angle theta, will get the new point that is called point P2 with its final coordinates x2, y2 and z2. So P1 with its initial coordinate x1, y1, z1, after rotation theta in anti-clockwise directions, we are getting the new point P2 with its final coordinates x2, y2 and z2. Now since rotation is carried out on z-axis, rotations which is carried out on z-axis, because Cn axis which is collinear with the z-axis. Okay, so since rotation is carried out on z-axis, therefore we can say that the z2 is equal to final coordinate z2 is equal to z1, because the position of z remain as it is. Therefore z2 is equal to z1. But what about the position of x1 and y1? Okay, so for change in x1 and y1, consider the two triangles. So these are the two triangles. Look at this triangle. This is the first triangle. This is first triangle. Look at this first triangle, and this is second triangle. Okay. So all of you look at this. This is first triangle and this is second triangle. So for to get the idea about what is the value of x1 and y1 after rotating on z-axis about an angle of theta, we are getting the new point P2 with its final coordinates x2, y2 and z2. Here the rotation is carried out on z-axis, therefore z2 is equal to z1. But what is the position of x1 and y1? What should be the value of x1 and y1? Consider the two triangles. This is the first triangle, this is the first triangle, and this is the second triangle. So for first triangle, look at this first triangle. What is the value of sine phi? So sine phi is equal to y1 upon r. Now first triangle with the angle phi. This is the angle phi. Okay. So what is the value of sine phi? So sine phi is equal to y1 upon r. Same way, what is the value of cos phi? Cos phi is equal to x1 upon r. Okay. You just focus on first triangle. This is the first triangle. With the help of this first triangle, what is the value of sine phi? Their angle of phi. What is the value of sine phi? Sine phi is equal to y1. This is y1 upon r. And what is the value of cos phi? Cos phi is equal to x1 upon r. So sine phi is equal to y1 upon r, and therefore in terms of y1, so y1 is equal to r sine theta. R sine theta. And cos phi is equal to x1 upon r in terms of x1. So this is a slight mistake is there, or is here. X1 is equal to r cos phi. This is equation 1 and this is equation number 2. Now here theta is a specified angle. So we have carried out the cyclic operations. We have carried out the cyclic operations up to theta degree in anti-clockwise rotations. So theta is a specified angle of rotations, whereas phi is an arbitrary angle. Phi is an imaginary, arbitrary angle. So now we consider the second triangle. Now we consider the second triangle. This is second triangle. Okay. What is the value of sine theta plus phi? So sine theta plus phi is equal to y2 upon r. And what is the value of cos theta plus phi? That is the value of x2 upon r. X2 upon r. So sine theta plus phi is equal to y2 upon r, and cos theta plus phi is equal to x2 upon r. So in terms of x2, that is x2 is equal to r cos theta plus phi, and y2 is equal to r sine theta plus phi. There is a one mistake here. Okay, we just ignore it. This is equation number 3. This is equation number 4. Now rearranging this equation number 3 and 4 using simple trigonometric relations. So here we are using simple trigonometric relations. So therefore x2 is equal to r cos theta plus phi. So while relieving this bracket, we can say that r cos theta into cos phi minus sine theta into sine phi. So therefore x2 is equal to r cos theta cos phi minus r sine theta sine phi. Same way, what is the value of y2 using simple trigonometric relations? So y2 is equal to r sine theta cos phi plus cos theta sine phi, and therefore y2 is equal to r sine theta cos phi plus cos theta sine phi. This is equation number 6. So these are the two equations 5 and 6. So you have to remember this. Now substituting this value of substituting the value of r cos phi and r sin phi from equation number 2 and 1 in equation number 5 and 6 respectively, we are getting x2 is equal to, instead of r cos phi and r sin phi, we are putting the value x1 and y1. So here you look at this, x2 is equal to x1 cos theta minus y1 sin theta. This is equation number 7. And y2 is equal to x1 sin theta plus y1 cos theta. So the equation number 8. So now we are having two equations 7 and 8. On expanding this equation for x2 and y2 and z2, okay, we are having two equations for x2 and y2, and for z2 we finally get x2 is equal to x1 cos theta minus y1 sin theta plus 0 z1. For y2 is equal to x1 sin theta plus y1 cos theta plus 0 z1, and for z2 is equal to 0 x1 plus 0 y1 plus 1 z1. So combining this equation to give a matrix equations. So x2 y2 z2 matrix is equal to cos theta minus sin theta 0, sin theta plus cos theta 0 plus 0 0 1. This is the matrix into x1 y1 and z1. So this matrix for C and Z, because the rotation axis which is situated on the Z axis, therefore this matrix for C and Z in an anti-clockwise directions. So in an anti-clockwise directions, the C and Z matrix, the value of C and Z matrix is cos theta minus sin theta 0, sin theta cos theta 0 0 0 1. Now to get the matrix corresponding to clockwise rotations, so previously we have derived a matrix C and Z for anti-clockwise. For clockwise directions, so instead of theta, we are putting minus theta. Okay, so while we are thinking about the clockwise directions, so instead of theta, we are putting a plus theta. Now it becomes minus theta. So minus theta, minus theta, minus theta, minus theta. So C and Z it becomes cos minus theta is equal to cos theta. Sine minus theta is equal to minus sine. So minus minus plus. So sine theta 0. Sine minus theta is equal to minus sine theta. Cos minus theta is equal to cos theta is 0, 0, 0, 1. So C and Z in a clockwise rotations, the value of C and Z matrix is cos theta sine theta 0 minus sine theta cos theta 0, 0, 0, 1. Same way. Similarly, it is possible to work out the matrix for Cnx and Cny. So suppose the rotation axis which is situated on x-axis. So what should be the matrix for Cnx? The Cnx value is 1, 0, 0, 0 cos theta sine theta, 0 minus sine theta cos theta. And same way for Cny matrix, cos theta 0 sine theta, 0, 1, 0 minus sine theta 0 cos theta. Okay. So while putting the value of theta, we can get the final matrix. For example, if we are thinking about the CNZ matrix, now n is equal to 0 or 360. Okay, so that means the theta value is 0 or 360. So C1 matrix, while putting the value of cos and sine, so cos and sine, the cos theta, while putting the value of cos 0 is equal to cos 0 is equal to cos 0 is equal to 1. So that means 1. Sin theta, sin 0 is equal to 0. That means 1, 0, 0. Sin 0 is equal to 0. That means 0. Cos theta and cos 1 is equal to cos 0 is equal to 1, 0, 0, 0, 1. So for C1 matrix, while putting the value of theta is equal to 0 or 360, the value of this C1 matrix is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. That is nothing but the E matrix. For C2Z, if theta is considered as 180 degree, so sin theta is equal to 0 and cos 180 is equal to minus 1. So C and Z. So sin theta, cos theta, so cos 180 is equal to minus 1. Cos 180 is equal to minus 1. So here minus 1, right? Sin 180 is equal to 0 and 0. Sin 180 is equal to 0. Cos 180 is equal to minus 1, 0, 0, 0, 1. So C2Z is equal to minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1. Same way for theta, if we are putting the value of theta is equal to 120 degree, if we assume theta is equal to 120, so sin 120 is equal to root 3 by 2 and cos 120 is equal to minus 1 by 2. So while putting this value, the matrix is minus 1/2 root 3 by 2. This is a little bit disturbed. This matrix is minus root 3 by 2 minus 1 by 2, 0, 0, 0, 1. And theta is equal to 90, then sin 90 is equal to 1 and cos 90 is equal to 0. So this matrix becomes 0, 1, 0, minus 1, 0, 0, 0, 0, 1. Okay. So we actually stop over here. I will stop my presentation over here. In my next video, I will discuss further.